So let's take a look at what's called the Henderson-Hasselbalch equation. Okay, let me back it up here just a second. What we're looking at here is as I add the acid and I add the base, what's going to happen is I'm going to change the pH. Remember, pH is what's changing. pH is either going to go up or it's going to go down depending on what happens. And remember, pH is essentially the negative log of the hydrogen concentration, right? So really what we're looking at when we look at pH changes is we're looking at concentrations of hydrogen changing throughout these problems. So we're constantly looking at H plus concentration ions either going up or going down. That's the general idea. Now when we solve, think about what we've been doing. We're doing this Ka expression where we have concentrate. Let me back it up again a little bit for you. So we have the weak acid dissociating into H plus and OA in the anion, right? The A would be your generic anion that I have. So what I would have is a Ka is equal to hydrogen concentrations times my anion concentration over this, right? We've been doing this pattern quite a bit. Now, what have we always been solving for? We keep solving for this over and over and over again, right? We've been solving for this hydrogen ion routinely because we want to take that hydrogen ion and turn it into pH, right? That's what we've ultimately been doing. So let's kind of cut to the chase and just focus on this ion instead of constantly plugging into this equation. Now what I could do is I can go ahead and solve for my hydrogen concentration just by using some algebra here and manipulating the equation. What I would end up with is Ka is equal to the concentration of the acid over concentration of the anion. Now why would I do this? Why would I use the equation in this format here? Well, if we go back to this buffer over here, wow, what a mess. What we've been looking at are these two things changing. Remember we looked at this changing here, right, that hydrofluoric acid and the conjugate base changing. We kept seeing that in both of these problems, these two were the things that were changing. Well, as a result of these two changing, we're going to get new concentrations of hydrogen ions every time. So as these two change, as my buffer gets used up, if my conjugate base gets used up and my acid goes up, as my conjugate base goes down and my acid goes up, well, that's what I'm looking at here, right? If my conjugate base goes down and this goes up, isn't that going to change my concentration of hydrogen? Because the Ka is always going to be the same. So by rearranging this equation, we can kind of see that change happening. Now, another useful thing that we can do is we can take the negative log of both sides. So if I take the negative log of this side, right, because we don't really care about the hydrogen, we're mostly looking at pHs. So if I take the negative log of both sides of the equation, what I would end up with is Ka minus the negative log of HA. I'm kind of using some properties of logs. If you don't remember your log properties, don't worry about it. You don't need to know. I'm just going to deriving an equation here for you. Alright, so over here what this would become, because I'm taking a negative log of the hydrogen concentration, is pH. This is a negative log of Ka. We would call that pKa. And then what I have here is I have the negative log, but I'm going to do is I'm going to make that positive. I'm going to reverse the sign notation. When I do that, I reverse these two. And what that means is the negative, or it's going to be the positive log, or plus the log, of the base over the acid. And this right here, my friends, is what's called the Henderson-Hasselbalch equation. I think I can call you my friends at this point, right? Okay. And get a little weird here because I'm tired. But this is the Henderson-Hasselbalch equation, and this little gem right here, seriously, this is a great little equation, can be used instead of the ice table. You can use or used instead of ice table. Now this only works for buffers, okay? So you have to have a buffer for this to work. Only for buffers. Why does this equation only work for buffers? Because you have to have the base and the acid together. You have to have the weak acid and the conjugate base. Okay, so I'm going to show you some calculations with this Henderson-Hasselbalch equation later, but the idea here is that we can plug in our Ka, figure out what the pKa is, figure out what our concentrations are, and then find out what our pH is. Then what we can do is we can add an acid or a base, a strong one, to the buffer, see how these two change, plug them back into this equation and see what my new pH is. Really is a nice little useful equation, and as I said in class and in other videos, I'll show you exactly how we use it numerically. Okay. Last thing I'm going to talk about is what's called a optimal buffer. All right, so pH is equal to the pKa, okay, plus the log of the acid concentration, I'm sorry, the conjugate base over the acid. Okay, so this is always going to be your base, by the way. Top one is always the base, the bottom one is always the acid. Okay, there is another version of this for POH. Don't use it, stay away from it. Always use this one. Always remember what this one is. Why? Because whether it's whatever base you have, you're always going to get the base on the top and the acid on the bottom. Always convert it to Kas. Don't go back and forth with them. All right, anyway, what is an optimal buffer? Well, an optimal buffer is one that will absorb the most hydrogen and hydroxides. Okay, optimal buffer essentially absorbs the most hydrogen and hydroxides. So what we want to have happen here is we want to have the buffer be able to absorb both acids and bases equally. So a buffer is optimal when these two concentrations are equal to 1. This comes up quite a bit in some of the calculations we're going to look at a little bit later. But when these two are 1, we're going to have a log here. If we take the log of 1, this is going to drop out. We're just going to have our pH is equal to our pKa at that point. Why is that important? It's important because what it tells us is that these two concentrations have to be equal to each other. That whatever this is has to be this. So what it means is that it can equally absorb the same amount of acid as it can base. Now remember, if I add it to this buffer solution, if I add HCl, this is an acid, it's going to react with that top portion, right? The HCl will react with A minus to make HA and Cl minus. Right? It's not going, well, the Cl minus isn't going to be a big deal, but it's going to absorb that hydrogen ion. This will go down. That concentration goes down. This then goes up because look, I'm making this go down and this go up, so therefore they will change. If I have a sodium hydroxide that I add, that sodium hydroxide is going to react with the acid, NaOH plus HA is going to give us H sodium iodide, or sodium whatever it is, whatever the anion would be. But again, notice what happens. This time my acid goes down and my conjugate goes up. You might want to get rid of the sodium here so you can see that in here. Right, sodiums don't do anything, chlorides don't do anything. Might be a little bit easier to see the actual reaction without them in there. Okay, so again, this goes down, this goes up. So optimal buffer means that these two are going to be equal to each other so that they can absorb equal amounts of acid and base. Once you add them, it knocks them out of whack. And eventually, if you keep adding enough of the acid, you're going to destroy the buffer and you're going to remove all of that anion. You're going to convert it almost all back to HA, to the weak acid. And that's what we're going to look at in a titration. A titration is a systematic way of looking at this system here. Okay, so I think I'm done talking. I think you can kind of get the idea of what I have here. So take a look at some other stuff. I'll see you in class. See you soon.